Hello and welcome back to the quiet cosmos. Tonight, the neutron star. We begin with a star that could no longer hold itself up and with a fall that stopped. Then the layers of what remained, from an atmosphere a few centimeters deep to a core whose composition is still argued over. After that, the magnetic field, and what such a field does to ordinary matter. Further on, the ones that are not alone, and what follows when a companion begins handing over its own substance. And at the end, two of them meeting, and the limit past which this state of matter is not held at all. Underneath all of it sits one idea. Ordinary matter is almost entirely empty space, and a neutron star is what is left when that emptiness has been taken away. Before we go on, if you enjoy this kind of unhurried astronomy, do consider a like or subscribe to the channel. It is a small thing, and it helps these long, quiet films find the people who are looking for them. The story starts long before the object itself exists, in the last hours of a very large star. A massive star spends its entire existence in a standoff with itself, pushing outward from the center exactly as hard as its own weight presses inward. The ones that end this way begin with something like 8 to 25 times the mass of the Sun, and for millions of years the arrangement holds without difficulty. In the core, hydrogen fuses into helium. When the hydrogen there is spent, the center contracts, warms, and helium begins fusing into carbon. The pattern repeats, each stage shorter than the one before it, each new burning confined to a shell around the last, until the innermost layer is producing iron. Iron is where the ledger changes sign. Every reaction up to that point released a little energy and paid for the support of everything overhead. Fusing iron takes energy in rather than giving it out. The support does not weaken gradually, it simply stops being paid. An account that has finally balanced to zero. The collapse that follows takes less than a second. The iron core at the center is roughly the size of the Earth, and once it can no longer carry its own weight, it comes together into a region a couple of dozen kilometers wide. Material at the leading edge of that fall reaches a noticeable fraction of the speed of light, and the whole passage from an Earth-sized ball to a city-sized one is finished before a second has gone by. Nothing in the star's long history happens at anything like this pace. Millions of years of steady fusion in the middle, and then a fragment of a second in which the geometry of the center is entirely redrawn. There is no noise to any of it, because everything above is still falling inward, and will be thrown clear before any sound could climb out. The quickest event ever to occur in that place happens where nobody can listen. What halts the fall is not a force in the ordinary sense, but a prohibition. Neutrons belong to a family of particles that cannot share the same quantum state. Two of them will not occupy the same condition of position and motion, and no amount of pressure persuades them otherwise. As the core is compressed towards the density found inside a nucleus, the available states run out, and the refusal to double up begins to behave like an enormous stiffness. The refusal does not work alone. At these depths, the force between the neutrons turns from an attraction into a hard shove outward, and without that shove, nothing of this mass could stand at all. This is not heat, and it is not burning. A star held up in this manner needs no fuel whatsoever and can cool for ages without shrinking, which is precisely what ordinary stars cannot do, since they stay large only by staying hot. This one stays large by counting, There are so many places and no more, and every single one is occupied. The floor it lands on is made of arithmetic and of force together. During those same moments, the composition of the core is rewritten from one end to the other. Under such pressure, the electrons are driven into the protons, and every one of those meetings produces a neutron and a neutrino, which departs at once. Material that began as a mixture of atomic nuclei and free electrons converts very nearly completely into a single species of particle. The count comes to something around 10 to the 57th, which, written out, is a 1 with 57 zeros after it, a number worth saying once and then setting down, because the meaning is far simpler than the digits. Everything the star had been in chemical terms, all the oxygen and silicon and iron assembled over its long lifetime, is reduced at the center to one kind of thing with one name. A whole star rewritten into a single word. The innermost part of the core overshoots its own equilibrium before settling. Infalling material carries momentum, and it does not halt precisely where neutron support becomes sufficient. It compresses a little past that mark and springs back outward again. The rebound runs straight into the layers still coming down, and the collision drives a shock wave upward through the star above. Left to itself, that shock would stall partway out. What carries it through is the flood of neutrinos leaving the center, which deposits enough energy behind the wave to keep it climbing until the outer star is taken apart and thrown clear. Everything above the core comes off in this one outward push, over a few hours, from an event at the center that lasted a fraction of a second. Everything visible afterwards traces back to that one reversal deep inside. One stroke of a bell, and never another. News of the whole event arrives first as neutrinos, rather than as light. Almost all of the energy released in the collapse, something on the order of 99 parts in 100, leaves as neutrinos, which pass out through the overlying star as though it were not there at all. Light has a far harder journey, since it must work its way outward through the material being thrown off, and it emerges only hours afterwards. In 1987, a star ended this way in a small companion galaxy of our own, roughly 168,000 light-years from here, and detectors buried deep underground on Earth registered a couple of dozen neutrinos from it. The optical discovery came later that same night. A handful of particles that barely interact with anything had carried the announcement across that distance and delivered it early. A message written in the thinnest ink there is. What survives at the center weighs between 1 and 2 times the Sun. Masses measured for these objects run from about 1.2 solar masses at the low end to roughly 2.1 at the high one. And the heaviest that we have measured with real confidence comes in a little above 2. That is a remarkably narrow band, given how varied the parent stars are. Something in the physics of the collapse funnels a wide range of beginnings into a similar outcome. How much of the original star finishes up in the remnant depends on how much material fell back afterwards and how much was carried away for good, and neither quantity is easy to predict from outside. The star that produced it may have been 20 times heavier than the thing it left behind. What remains is a signature, kept back after the letter itself was sent away. All of that mass sits inside a sphere about 24 kilometers across. For a body of roughly 1.4 solar masses, the best measurements currently available place the radius between 11.8 and 13.4 kilometers, which gives a width somewhere in the range of 24 to 27 kilometers overall. Those figures did not come from any telescope resolving a disk, because no telescope can resolve one. They come from an X-ray instrument mounted outside an orbiting station, which reads the precise shape of the light arriving from hot patches on the surface and works backwards from that shape to a size. A point the width of a small city at the end of a very long sentence. The density of this material is the density of an atomic nucleus. 1 cubic centimeter of it holds close to 270 million tons. That figure is not what you get by compressing ordinary material especially hard. It is what you get by removing the emptiness from ordinary material altogether. An atom is overwhelmingly vacant. A nucleus with a diameter some tens of thousands of times smaller than the atom built around it, and electrons spread thinly through the remaining volume as a matter of probability. Everything solid you have ever handled owes its solidity to those electrons keeping their distance from one another. Take that arrangement away, and the volume drops enormously, while the mass stays exactly where it was. Here the distance has gone. The nuclei have merged into one continuous medium, and what is left is nuclear material in bulk quantity. The inside of an atom, grown until it is wide enough to walk across. A teaspoon of that material would weigh about 1,000 million tons. 5 milliliters is a modest measure by any domestic standard, and at nuclear density, that spoonful comes out at the weight of a small mountain. That comparison is worth a moment, since a spoon is an object anyone can hold, and a mountain is emphatically not. Nothing on this planet is available for comparison. The densest metals we have, osmium and iridium, fall short of it by a factor of more than 1 million, and they are the extreme end of what ordinary chemistry can produce. The spoonful is a piece of arithmetic rather than an object that could ever exist, since the material would not hold together outside the star and would come apart the instant it was lifted out. The arithmetic, though, is exactly the point. Mountains fold down small enough to sit in a spoon. This is the densest arrangement in which material is still recognizably material. Below the surface of such an object, everything that could be pressed out has already gone. The space inside atoms, the space between neighboring nuclei, the space that gives an ordinary solid its volume. What is left has no give in it anywhere. Pressing on it harder produces almost no change in volume at all. Adding further mass does not compress it a great deal because there is very little room left to compress into. Instead, the addition pushes the whole body towards a boundary of an entirely different kind, beyond which nothing stable survives, and the object stops counting as a star. Between that boundary and the last arrangement the electrons alone can hold up, there is exactly one place to stand, one stable configuration, and this is it. The final address at which matter can still be registered under its own name. Gravity at that surface runs about 200,000 million times stronger than it does here. The figure follows directly from the two numbers already given. A sun's worth of mass, or rather more, gathered inside a dozen kilometers of radius. What that means in practice is hard to hold in the head, so a small example helps. An object released 1 meter above such a surface would arrive traveling at about 2,000 kilometers per second, having crossed that single meter in a millionth of a second. Nothing of ordinary size would keep its shape on arrival, and nothing built on a familiar scale could stand there to begin with, since the same gravity flattens whatever it holds into a smooth, even shell. That one condition shapes everything else about these bodies: their form, the thinness of their outer layers, the absence of terrain. A slope with no gentle section anywhere along its length. Leaving such a surface would take a speed of roughly half that of light. Escape velocity, the speed at which a thrown object never returns, is about 11 kilometers per second on Earth and around 600 kilometers per second at the surface of the Sun. Here the number is comfortably over 150,000 kilometers per second, more than half the speed of light, and fast enough that the ordinary schoolroom formulas stop being accurate and have to be replaced by their relativistic versions. Put another way, the energy needed to lift a single kilogram clear of that ground is beyond anything our chemistry can supply. Light itself gets away without trouble, but not without cost, and the nearer a body of a given mass comes to this condition, the steeper that cost becomes. Only light can pay its way through that door. Because the geometry around it is bent, more than half of the surface can be seen at once. Light leaving a patch on the far side, which, by straight-line reasoning, ought to depart harmlessly sideways and never reach us, is curved around by the gravity it is climbing out of, and delivered instead to an observer in front. The visible face is therefore not a hemisphere, but something distinctly larger, with parts of the far side folded into view around the edges. Exactly how much more depends on how compact the particular body happens to be, and it differs from one object to the next. So the honest way to state it is as a direction rather than as a fixed fraction. A more compact star shows rather more of itself. This same bending is what makes the measurement of size possible at all. A sphere quietly displaying part of its own reverse. Light that does get away arrives carrying less energy than it set out with. Climbing out of that gravity costs a photon something. And since a photon cannot travel any slower, it pays in wavelength instead. The whole spectrum turns up, stretched towards the red by something in the region of a quarter. Spectral lines, whose positions laboratories know to great precision, appear shifted by that amount, and the size of the shift depends on nothing except the ratio of mass to radius. That turns the effect into an instrument. Find a line you recognize, measure how far it has moved, and you have constrained how much mass is packed into how small a sphere, without ever seeing the sphere itself. It is one of the few pieces of information about the interior that reaches us intact, carried in something as unremarkable as the position of a colored line. Color handed over as a toll on the way out. Clocks on that surface would run more slowly than clocks far away from it. This is the same effect as the reddening of the light viewed from the other side. A wave arriving stretched is a wave whose crests were emitted more slowly than a distant observer's own timepiece counts them out. The difference here is not a laboratory subtlety of a few parts in a billion, the sort that navigation satellites above the Earth have to allow for in their software. It is large enough to be read straight off the spectrum, and large enough that anyone modeling what happens near such a surface has to carry the correction through every step of the calculation. A century measured down there is not a century measured out here. This is not a matter of instruments performing badly. The interval between two events genuinely differs depending on where it is counted. The clock runs slower there, and there is nobody to correct it. No laboratory on Earth can manufacture this material, although the attempt is instructive. Accelerators that collide heavy ions head-on do briefly reach densities in the same neighborhood, inside the tiny fireball where two nuclei overlap. The time available is on the order of the interval in which light crosses a single atomic nucleus, and the volume involved is smaller than one atom. From that flicker, physicists extract what they can about how nuclear material behaves when it is compressed. Inside one of these stars, the same condition is simply maintained, at a scale of tens of kilometers without interruption for millions and often thousands of millions of years. What separates the two situations is not the density, but the duration and the scale. And that is why the stars remain the better laboratory. The experiment has been running there since long before there were any trees on this planet, and nobody has to hold the apparatus together. How matter behaves at that depth is still an open question. The relationship between pressure and density inside such an object, known as the equation of state, cannot be derived from first principles with any confidence, because the calculation involves many-body nuclear physics in a regime no theory has yet been tested against. Several competing versions exist side by side. Some are stiffer, meaning the material resists compression more strongly, and the star finishes up slightly larger for a given mass. Others are softer and predict a smaller body. This is why each radius measurement carries so much weight. An object of known mass and measured size rules some versions out and allows others to survive another round. The interior itself stays permanently out of reach, and until the question closes, every description of what lies down there carries a quiet qualification along with it. A locked book whose binding alone has been measured with great care. There is a second route to the same condition, and it involves no massive star at all. A white dwarf, the compact remnant left behind by a far smaller star, is supported by its electrons in much the way this object is held up by its neutrons. When such a dwarf sits beside a companion and draws material away from it, its mass creeps upward towards a ceiling near 1.4 times that of the Sun. Most of the time, the outcome is a thermonuclear explosion that unbinds the entire body. Under certain conditions, though, the electrons are absorbed into the protons instead. The support gives way quietly, and what emerges is a neutron star with no massive parent anywhere in its history. Telling this path apart from the ordinary one is difficult long afterwards, since the product looks much the same either way. The scenario is regarded as possible. Clear examples are scarce. Another door into the same room. In its first hours, the new object is hotter than almost anything else we know of. The interior emerges from the collapse at tens of thousands of millions of degrees. Within minutes, that has fallen to something near 1,000 million. And it falls not by radiating heat away in the familiar sense, but because neutrinos stream freely out of the interior and carry the energy off wholesale. After that, the pace changes altogether, and what follows is a cooling that runs for millions of years, and then for longer still. During that long decline, the material inside sorts itself out, denser and lighter forms separating by depth, until the object has a definite internal structure with distinct layers, each with its own rules. Very little else in nature spans such a range within the life of a single body. A few minutes of enormous heat, and then an evening 1,000,000 years long. This body is arranged in layers, much as a planet is, except that each layer obeys rules that do not apply to the one above it. Moving from the outside inwards, one passes through an atmosphere, a thin outer envelope, a solid crust, an inner crust, an outer core, and at last an inner core whose composition is still unsettled. What makes the arrangement unusual is its compression. On Earth, an equivalent sequence of shells is spread through thousands of kilometers of depth. Here, the whole structure is folded into the first few kilometers below the surface, and most of the important transitions occur within the first one. Every boundary marks not simply a change of material, but a change of the physics in charge of it, so that a traveler going inwards would cross out of chemistry into nuclear physics, and then into territory no laboratory has reproduced. It is less one object than a set of rooms, and in each room a different law holds the keys. The atmosphere that covers this surface would sit comfortably in the palm of a hand. Measurements and models put its depth at somewhere between 1 and 10 centimeters for a typical object, thinning to a few millimeters on the colder examples, and swelling to a few tens of centimeters on the hottest. It is not air in any familiar sense. Gravity, strong enough to flatten everything beneath it, leaves no room for a deep envelope of gas. So what survives is a shallow shell of plasma, most often hydrogen or helium, drawn from material that settled onto the star after it formed. The gas is fully ionized. The electrons are separated from the nuclei, and the whole layer is held down so tightly that its density changes enormously across a distance you could measure with a ruler. Every function an atmosphere performs elsewhere in the universe is performed here within the thickness of a finger laid flat. A whole sky, and it fits in one hand. Thin as that layer is, it decides what the star looks like to our telescopes. Radiation rising from the surface has to pass through the plasma before it leaves, and in passing it is scattered, absorbed, and re-emitted. So the X-ray spectrum that finally reaches us is shaped in the last centimeter of the journey, rather than in the enormous interior below. Astronomers, therefore, cannot read a surface temperature directly. They must first assume a composition for the atmosphere, hydrogen or helium or something heavier. Build a model of how that composition would redistribute the outgoing energy, and only then convert the observed spectrum into a temperature. Choose a different composition, and the temperature derived shifts with it, which is one reason published values carry generous uncertainties. A layer only a few centimeters deep, therefore, stands between us and every number we quote about the surface. A pane of window glass doing the work of an entire climate. Below the plasma there is neither gas nor liquid, but solid ground. The crust begins almost immediately and continues down for about a kilometer, and through its upper reaches the material is a metal in the strictest sense of the word. Nuclei of the ion group arranged in a regular lattice, with electrons flowing freely between them. The word solid, however, needs care. This is not rock and not steel. The lattice is held together by pressures that no anvil on Earth could imitate, and the electrons wandering through it move at a substantial fraction of the speed of light. Nothing in this layer can corrode because there is no free oxygen and no chemistry left to speak of, and nothing can weather it because there is neither wind nor water. The iron simply stays where the pressure put it, unchanged for as long as the star endures. That iron ground will never rust. That lattice orders itself far more perfectly than the jumble of small grains found in ordinary metals. Ordinary iron on our own planet is a mosaic, countless tiny crystals pressed against one another, and the seams between them are where the metal eventually fails. Even so, simulations do find grains and seams here as well, but they matter far less. The boundaries weaken the material only slightly, and a crack cannot run along them the way it runs through steel. The composition also changes with depth. Near the top, the lattice sites hold iron group nuclei. Further down, as the pressure mounts, the favored nuclei grow steadily heavier and steadily richer in neutrons, so that the crystal quietly rewrites its own chemistry as one descends. Its density climbs from something comparable to ordinary metal at the surface to values at the base of the crust that no material on Earth approaches. A crystal whose seams are barely a weakness at all. The outer surface is smoother than anything our workshops know how to polish. Gravity at that boundary is so overwhelming that any material standing proud of the sphere is pulled back into line almost at once. And the equilibrium shape that results departs from a perfect sphere by no more than a millimeter or so in most calculations. A billiard ball, which we treat as a byword for smoothness, is by comparison a rough thing. Scaled up to the same diameter, its bumps and hollows would tower over anything found here. No erosion is involved, no grinding and no polishing. The evenness is simply what the balance of forces permits, achieved the moment the surface hardened and held ever since without effort. Any process that might roughen it is outmatched by the pull holding it flat. Nothing is left to add to that surface. The tallest elevation anywhere on such a star falls short of a millimeter in most calculations. And even the most generous models allow only something of the order of a centimeter. Astronomers still call these features mountains, partly out of habit and partly because they matter. A bump of that scale on a spinning body would be worth searching for. Building one is the difficulty. To raise it, the crust must hold weight against a pull some 200,000 million times stronger than the pull that holds us to the ground, and the material gives way long before a hill of any consequence can accumulate. What remains are wrinkles on the scale of a grain of sand, spread over a sphere some 24 kilometers across. A walker would step over that whole mountain range without noticing it. Strength here is measured not in tons per square centimeter, but in how far the material can be deformed before it yields. And by that measure, the crust can be strained by roughly 1 part in 10. Familiar materials fail far earlier. A steel bar bends a small fraction of a percent. Then a crack begins somewhere at a floor, spreads from that floor, and the bar parts. Simulations that followed millions of nuclei one at a time found that the crust does not behave in that way at all. The seams that do exist are barely weaker than the material around them, so the whole lattice takes the load together and continues to take it until the deformation reaches about 1/10, at which point it gives way everywhere at once. By that yardstick, it is the strongest material known to us. A wall that bends further than any other before it finally lets go. Deeper down comes a threshold at which neutrons stop staying inside nuclei. As the pressure rises, the favored nuclei take on more and more neutrons, and at a certain depth they can hold no more. The additional neutrons begin to leak out into the space between the lattice sites, where nothing binds them to any particular nucleus. Physicists call the process drip, which is an unusually literal name for something so far outside ordinary experience. Below that boundary, the material has a character with no counterpart anywhere else. The lattice is still there, still ordered, still a solid by any reasonable definition. But it is now immersed in a sea of free neutrons that flows around and between its sites. Two states of matter occupy the same volume, without either giving way to the other. It is a threshold past which the nuclei stop keeping what belongs to them. Further in still, computations predict material that has given up the shape of separate spheres altogether. Squeezed together and pulled apart by the competition between nuclear attraction and electrical repulsion, The nuclei are calculated to merge into long rods, then into flat sheets, then into tubes and cavities, each geometry taking over as the density climbs. The region is no curiosity at the margin. Models place perhaps half of the entire mass of the crust inside it, packed into something like a fifth of its thickness. None of this, however, comes from a telescope. All of it comes from a computer. There is no direct observational confirmation that any of these structures exist, no experiment on Earth that reaches the required density, and no prospect of an image. The case for them is that several independent calculations, starting from different assumptions, arrive at much the same conclusion. Nobody has seen the shape, and everybody has worked it out. The names given to those structures are the most domestic in all of physics. When the calculated shapes were first plotted, they resembled food closely enough that the researchers reached for the kitchen. The small blobs became gnocchi, the long rods became spaghetti, the flat sheets became lasagna, and the tubes and bubbles picked up culinary labels of their own in turn. The whole family is known collectively as nuclear pasta, and unlike most jokes of that kind, the term did not stay in the corridor. It appears in the titles and abstracts of serious papers to this day, and nobody has proposed anything better. The standing of the physics behind the names has not changed. It remains a prediction, argued for by simulation and supported only indirectly, and the real interior may yet arrange itself in some other way entirely. The warmest words in the whole theory of dense matter. Beneath the crust lies an ocean made almost entirely of one ingredient. In the outer core, the accounting is straightforward by the standards of this subject. About 95 parts in 100 are neutrons, and what survives beside them is a small admixture of protons with an equal number of electrons, present because the balance of nuclear reactions insists on a residue of charge. The density has already passed the density inside an atomic nucleus, so the neutrons are no longer arranged into anything at all. They simply fill the volume, touching everywhere, with no gaps and no structure. On Earth, the deep ocean varies with depth in salinity, in temperature, and in the life it carries. This one has none of those distinctions to offer. From where the solid layer ends to whatever begins at the center, the recipe barely changes. A sea whose composition drifts by degrees and never by kind. That neutron liquid is, in all probability, a superfluid. A superfluid flows without friction. Once set moving, it keeps moving, since there is no viscosity to take the energy away. And laboratory helium, cooled to within a few degrees of absolute zero, does exactly this. The interior of a star, at temperatures beyond 100 million degrees, would seem an unlikely place for such behavior. Yet the enormous densities allow neutrons to pair up in a way that produces the same outcome. Our best evidence is indirect. An X-ray observatory followed the young remnant in Cassiopeia, whose age is put at around 330 years, for a decade, and recorded a drop in temperature of roughly 4% across that interval. The simplest reading is that the neutrons were entering the superfluid state during those very years, although other readings are argued for. The current has forgotten how to slow. The protons sharing that volume are thought to be superconducting. Being charged, they pair in much the same manner as the neutrons do, and a fluid of paired charges carries electric current with no resistance whatsoever, which means that currents, once established in the core, have no obvious reason ever to decay. On Earth, superconductivity is a phenomenon of extreme cold. The best laboratory materials demand temperatures far below anything our planet offers naturally, and the whole technology is built around refrigeration. Here, the same behavior is expected at temperatures well above 100 million degrees, which makes this the hottest superconductor anyone seriously discusses. The reason is not warmth but density, since pairing depends on how tightly the particles are packed against one another, and in this material they are packed as tightly as matter allows. A circuit that costs nothing to run. What occupies the very center is genuinely unknown. Several candidates are on the table and each has serious support. The simplest is that the neutron liquid continues unchanged all the way in, merely denser than above. A second possibility is that the pressure makes it favorable for some neutrons to convert into hyperons, heavier relatives that ordinarily decay within a fraction of a microsecond, but which would be stable in a place where every lighter slot is already occupied. A third holds that particles called mesons form a condensate, a collective state in which enormous numbers share a single quantum condition. The trouble is that all these possibilities produce stars of broadly similar size and mass. So the measurements available to us do not discriminate between them, and the models diverge precisely where no instrument can follow. It is the one room in the house with no window in it. It is also possible that quarks down there are no longer assembled into particles. Ordinarily, quarks are never found alone, only bound together in 2s and 3s, and no experiment has ever isolated a single one. The force between them grows stronger with distance, so pulling them apart is not something that can be done. At densities several times that of an atomic nucleus, however, the groups would be pressed so closely against one another that the question of which quark belongs to which neutron loses its meaning, and the material may become a continuous medium of quarks, moving freely through the whole volume. A number of respectable models allow for such a core. Others do without it entirely, and present observations cannot yet tell the two families apart. Whether the star has a bottom or a further bottom below that stays open. There may be one more floor beneath that one. Heat leaves this object only through a barrier a kilometer thick. Inside the core, the temperature may run to hundreds of millions of degrees. At the surface, for a star of middle age, it is nearer 1 million, and the entire drop occurs across the crust. The gap is maintained by how well or badly that layer conducts, and conduction there is carried out chiefly by the free electrons moving between the lattice sites, which are impeded by impurities, by irregularities in the ordering, and by whatever strange geometries occupy the deepest part. This is why the crust is studied through its warmth. By taking the surface temperature of stars of known age and comparing the sequence against models, physicists work backwards to the properties of a layer nobody can sample. A blanket measured only on its outer side. Now and again, the strain stored in that layer lets go, and the episode is called a starquake. Stresses accumulate because the crust is rigid, while the star it encloses slowly changes shape, and eventually some region reaches the limit the lattice can bear. The displacement that follows is tiny by the standards of geology. A shift that models put at well under 1 millimeter is enough to constitute a major event, since the energy held per unit of movement in such material is beyond comparison with anything on our own planet. The energy comes out as X-rays and as a rearrangement of the magnetic field rather than as sound, because a vacuum contains nothing to carry sound away, and because the atmosphere above is a few centimeters deep and could transmit very little in any case. All of geology fitted inside 1 millimeter. After the largest of these episodes, the crust appears to ring for a while. In the fading light that followed, an enormous outburst from one of these stars in 2004 Analysts sifting the X-ray record found the brightness rising and falling at several steady frequencies, persisting for minutes after the main event had passed. The most natural reading is that these are the normal modes of the crust itself, the particular tones a shell of that composition and that thickness is able to sustain, much as a bell will only sound the notes its geometry permits. If the reading is correct, the frequencies become an instrument, since the tones depend on how thick the layer is and how stiff it is, and both quantities are otherwise beyond reach. Alternative explanations exist, and the debate has not closed. The note may yet tell us how thick the shell is. Everything described so far belongs to the first kilometer. The atmosphere, the outer envelope, the lattice, the drip point, the calculated geometries below it, all of that architecture with its succession of separate physical regimes is contained in a shell no thicker than a modest hill is tall, and it accounts for about 1% of the star by mass. The remaining 99 parts are core, uniform to a first approximation and largely beyond our reach. Yet the thin outer shell earns its place in the accounting because the electric currents flowing through it are among the things that sustain the magnetic field we detect from outside. And that field is how most of these objects announce themselves to us at all. The thinnest part of the structure is the part that speaks, a whole world of arrangement folded into the opening kilometer. The magnetic field of a neutron star is not something the object manufactures for itself. It arrives as an inheritance from the star that came before. An ordinary massive star carries a field that is, by our standards, unremarkable, spread thinly across a body far wider than the Sun. When the core gives way and falls inward, the field lines are carried along with the matter they thread, and the same lines that once covered a broad face are gathered onto a surface the width of a city. A core, roughly as wide as the Earth, ends as a body about 24 kilometers across, and everything that was written on the larger sphere is now written on the smaller one. Calculations suggest the concentration raises the strength by a factor of some hundreds of thousands, although the exact bookkeeping depends on how faithfully the lines stay tied to the matter. For most of these stars, nothing new has to be made in that moment. What it inherited was never spent, only condensed. Ordinary neutron stars carry fields that outmatch anything we are able to arrange on our own planet. The magnetic field at the surface of the Earth measures about half a Gauss, a quantity so mild that a compass needle answers to it lazily and nothing else notices it at all. A typical member of this population sits somewhere between 100 million and a million Gauss, which is to say hundreds of millions to a couple of million times the value we live inside. The strongest fields we have ever produced, in experiments that destroy their own apparatus as they run, still fall short of the bottom of that range by something like a factor of 10 and cannot be held for more than a flicker. Against the upper end, there is no comparison to be made at all. Astronomers seldom quote these numbers as multiples, since a multiple stops being informative once it has grown past a few million. They count the digits instead, a difference no longer measured in multiples, but in zeros. Every such field has two ends, and neither of them is obliged to line up with anything else about the star. To a first approximation, the arrangement is a dipole, the same shape a school magnet makes in iron filings, with lines leaving one pole, arching far out into space, and coming back down to the other. What matters is that the axis joining those two poles is usually tilted with respect to the geometry of the body itself. So the magnetic ends and the shape of the sphere quietly disagree with each other. That disagreement is not a flaw in the description. It is the reason many of these objects are visible to us at all, because whatever energy escapes does so preferentially along the magnetic axis, and an axis set at an angle sends that outflow into directions an observer may happen to occupy. The map has two ends and no middle. When the narrow beam that leaves those magnetic poles sweeps across the position of the Earth again and again, the object acquires a particular name. We call it a pulsar. The word is often taken to describe some special behavior, and yet it describes nothing of the kind. Two similar stars may sit in the same region of the galaxy, and one of them will be catalogued under that name, while the other is never listed at all, purely because the geometry favored us in the first case and not in the second. The name is a record of our vantage point and of very little else. Just a name earned by where we happen to stand. One extreme variety carries a field about 1,000 times stronger again, and the objects that do so are called magnetars. The strength measured at the surface comes out near 1,000 million times the field of our own planet. And when the energy of the largest outburst known to us is accounted for, the internal field required is higher still, though that inference depends on a chain of reasoning rather than on a direct reading. About 30 such objects have been identified so far, a figure that creeps upward by one or two as surveys continue. That is a small enough number for the community to keep them individually, each under its own catalogue designation, each with its own history of quiet decades and occasional activity. The true population is almost certainly larger than the list, since an object of this kind that has never been active would be difficult to notice. The list is still short enough to be kept by hand. Chemistry itself changes in a field of that strength, and it changes in kind rather than in degree. An atom held in ordinary surroundings is very nearly a sphere, because the electrons answer to the pull of the nucleus and to almost nothing else. Set the same atom in the field of a magnetar, and the magnetic influence no longer competes with the electrical one, but overrules it. The electron clouds are drawn out along the lines and narrowed across them, so that atoms become elongated spindles instead of balls. Binding energies climb, and computations indicate that long chains of atoms strung end to end along the field lines would hold together in ways that have no counterpart in any laboratory here. None of this has been observed. It comes from theory and from numerical work, and the surface where it would apply lies far below anything our telescopes can resolve. Chemistry written in a different alphabet. Near a magnetar, even empty space gives up its ordinary behavior. Theory, worked out in the 1930s, predicts that a sufficiently strong field makes the vacuum optically uneven, so that light moves at very slightly different speeds depending on how its oscillation is oriented, and light traveling through emerges with its polarization turned. In our own laboratories, the effect is so slight that no apparatus we possess has ever registered it. In 2016, a team measured the light of a nearby isolated neutron star, one with a strong field of its own, though not a magnetar, using a large telescope, and found the polarization strongly aligned, which is what the prediction requires. The object was faint, the measurement demanding, and the result is best described as an indication rather than a confirmation. Further observations are still being gathered. It remains one of the few places where a purely theoretical property of empty space can be examined at all. Emptiness that may yet turn out to have a grain. The largest store of energy aboard such a star is neither fuel nor leftover warmth, but the field itself. In an ordinary star, the accounting is straightforward. The reserves sit in the nuclei waiting to be released, and the magnetic contribution is a rounding error at the bottom of the ledger. Here, the ledger is inverted. The energy held in the field of a magnetar exceeds the thermal energy still stored in its interior, and there is nothing being fused to add to the total, since the material was converted long ago into a form that will not burn. Everything such an object does over the following thousands of years, every emission and every disturbance of its surroundings, is drawn from that single account. This is why the class was named after magnetism when it was first proposed. The purse weighs more than everything else its owner has. A magnetar shines mainly because its field is slowly rearranging itself. The currents that maintain a field of that size run through the crust, and they do not run without loss. Across centuries, the configuration works its way towards a simpler one, giving up energy as it goes, warming the crust from beneath and holding the surface temperature above what the cooling history on its own would allow. The output emerges mostly in X-rays and can hold up over long stretches of time. An ordinary neutron star has no such reserve in its crust and simply grows colder from the day it is made. Nothing is falling onto the star from outside, nothing is burning. The object is lit by the gradual undoing of its own geometry, which is an unusual source of light by any standard, and a remarkably durable one because the reserve is large and the leakage is unhurried. A lamp that runs on its own shape. These objects send out short, soft bursts from time to time, and the pattern of them is distinctive enough to have supplied the class with its earliest name. A single event lasts roughly 1/10 of a second, and by the standards of the object producing it, the amount of energy involved is trifling. They seldom come singly. An object will produce a handful within an hour, then dozens across a few weeks, then nothing whatever for several years. And afterwards, the sequence begins again, without any warning we have learned to read in advance. The radiation sits at the soft end of the gamma range, which is how the label soft gamma repeater came about, coined before anyone knew what the sources were. Decades of monitoring have built up long records for a small number of them, and most of what those records contain is silence. Short letters exchanged for years on end. On the 27th of December 2004, one of these objects gave up a far larger share of its reserve than usual, and the whole of it was over in about 1/5 of a second. In that fraction of a second, the star put out as much energy as the sun emits across 250,000 years. Some analyses of the same records place the total 2 or 3 times higher. The number depends on assumptions about how the emission was spread across the sky, so it is offered as an estimate rather than as a reading off a dial. The event was not an ending of any kind. The object is still catalogued, has been watched many times since, and carries on much as before. It settled its field once, thoroughly, after a long stretch of very small adjustments. An old star cleared its throat once and went back to what it had been doing. Instruments on Earth registered the arrival of that light, which is a peculiar thing to be able to say about something on the far side of our own galaxy. The radiation reached the upper atmosphere and briefly altered the properties of the ionosphere, the thin conducting layer from which long-wave radio signals bounce, and the alteration was pronounced enough to show up in the records of equipment that monitors the terrestrial field for entirely domestic purposes. Several spacecraft detectors were overwhelmed at the same moment and had to be calibrated afterwards from the shape of their own saturation. Nobody on the surface noticed a thing, and nothing on the surface was affected. The entire disturbance lived inside the readings. The light had been on its way since long before there was anyone here to keep instruments at all. Distant weather traced all the same from the movement of a needle. The cause of such an event is understood as a rearrangement of the field, with the crust following it rather than resisting indefinitely. The lines are anchored in the solid outer kilometer, and as the interior configuration works towards a lower energy arrangement, the anchored ends are pulled with it. Strain accumulates in the crust over decades or centuries, a little at a time, until the material yields somewhere and shifts by a small amount. That small displacement lets the lines above reconnect into a simpler pattern, and the energy stored in the old pattern leaves the star. Neither half of the process acts on its own. The field cannot rearrange while the crust holds it, and the crust does not move unless the field asks it to. The accumulation takes a human lifetime. The release takes a fraction of 1 second, a knot coming undone in a rope as long as a continent. Around the star, the field maintains a shell of charged particles that belongs to it entirely. This is the magnetosphere, and the amount of material in it is negligible by any ordinary measure, a mere trace spread through a volume larger than the Earth. Yet it is not shapeless. Its form is dictated by magnetic geometry instead of gravity. Particles travel freely along a line and are almost unable to cross from one to the next. So the whole envelope is organized into shells and channels that follow the field exactly. Currents run through it, and the particles filling it are drawn up from the star itself rather than gathered from the surroundings, which is one reason so little material is needed to make the structure work at all. In the magnetars, the envelope is twisted rather than simple, which is one of the things that distinguishes them, and the twist stores energy of its own. This envelope is held by lines rather than by weight. Heat and charged particles are funneled by that geometry onto small patches near the magnetic poles, and those patches end up warmer than the ground around them. Inside the crust, heat travels much more readily along the field lines than across them, so the interior warmth is guided to the places where the lines meet the surface instead of spreading evenly. Particles returning from the magnetosphere land in the same neighborhoods and add their own contribution. Because the patches occupy so small a share of the total area, they account for very little of the surface and for a great deal of what an X-ray telescope actually collects. The patches are modest in size, from a few hundred meters to about a kilometer across, on a body some 24 kilometers wide. And they can be noticeably hotter than the surface as a whole, hot enough to give off X-rays, while the surrounding ground gives off very little. Warm coins on cold ground. From the shape of the light those warm patches deliver to us, the size of the star underneath them can be recovered. The gravity at the surface is strong enough to bend the star's own light around the body. So a patch stays partly in view, even after it has passed what would otherwise be the horizon. And more than half of the sphere is presented to us at once. How much light leaks around in that way is set by the ratio of mass to radius, and it leaves a signature in the brightness we receive. Astronomers build computed signals for many combinations of mass and radius, compare them with the arriving one, and keep the combinations that survive. Applied to the heaviest such star we have measured, the method returns a radius near 12 4/10 kilometers, give or take about a kilometer. The instrument never sees a disk. The size is read out of a shadow. Careful work on the same observations produced a result nobody had ordered. The warm areas are not arranged opposite one another. A simple dipole would place them at two antipodal points, one on each side of the body, and the arriving light fits that arrangement poorly. Though more than one alternative survives the test, the fits prefer patches sitting closer together than opposite, with shapes that are drawn out rather than round, and at least one of them well away from where a textbook would put it. If those warm areas mark the footprints of the field upon the crust, then the field itself is not the tidy two-ended figure of the school demonstration. The finding emerged from data gathered with an entirely different question in view, which is how a good many such things arrive. The real configuration appears to have additional poles and no symmetry worth speaking of, which is what theory had always allowed, and what nobody had previously been able to demonstrate. Two ends that turned out not to face each other. Where the strongest fields come from is an argument that has not been settled. One account has the field made on the spot. In the first seconds of the remnant's life, the interior is enormously hot and churns over on itself, and a churning conductor can multiply a modest field by an extraordinary factor in very little time. The competing account needs no such machinery and says the field is simply carried over from a progenitor that was unusually magnetized to begin with, of which a few are known. Both stories arrive at roughly the numbers we observe, which is exactly the difficulty. Neither can be ruled out by the strengths alone. The seconds in question happened long ago, inside an opaque object, and were witnessed by nobody. Deciding between the two would need evidence of a kind we do not currently possess. The question stays shut in a strong box for now. What looked like a firm partition between the classes has softened into a gradient. For a while, the arrangement looked tidy. Ordinary objects on one side with modest fields and modest behavior, magnetars on the other with enormous fields and occasional activity, and a clear gap between. Then a source turned up with a surface field no larger than an ordinary one, which nevertheless produced the short outbursts and the X-ray output characteristic of the other group, and it was followed by others. Meanwhile, several strongly magnetized objects have been watched for years without doing anything at all. The current explanation is that what matters is the field hidden inside the crust, rather than the one measured outside it, and the two need not agree. The tidy division has quietly become a matter of degree, a line that turned out, on closer inspection, to be a slope. Some of these stars are visible to us by their own warmth and by nothing else. They emit no beams that reach us. They have never produced an outburst, and they are found only because a soft X-ray glow from a hot surface stands out against an empty patch of sky. A small group of them is known, discovered by an orbiting survey and studied since, and they are among the least dramatic objects in the catalog. No companion, no material falling in, no activity of any sort, only a body cooling on its own schedule. The closest of them, and the closest such star known to us anywhere, lies about 400 light-years away in the constellation of the Southern Crown, with estimates ranging from 350 to 450. Solitude of that kind, though, is not how most of these stars begin. A warm stone found in a dark room. Very massive stars are seldom born alone. Surveys of hot, heavy stars keep returning the same result. The majority of them have at least one companion, and a good number belong to systems of 3 or more. This is not a curiosity of a few unusual regions of the sky. It follows from the way such stars form, out of the same collapsing knot of gas and dust, where a single dense core tends to break into pieces rather than draw everything into one body. The two fragments settle into orbit around a shared center and pass their short lives within reach of each other, exchanging light and, in some cases, material. Because stars of great mass are precisely the ones that end as neutron stars, this arrangement matters for everything that follows. The object left behind at the end usually has something else nearby. Pairing is not an exception. It is a habit the galaxy has kept up for a very long while. When the core of such a star gives way, the partnership it belonged to is usually undone. A large share of the star's mass is thrown outward in a short time, and the gravitational hold that kept the two bodies together weakens along with it. The companion, still traveling at the speed its old orbit demanded, finds itself circling far less material than before. There is a second effect as well, because the collapse and the outgoing shell are never quite symmetrical, so the newborn remnant almost always receives a push at birth and leaves the scene carrying that push with it. Between the lost mass and the sideways shove, most systems come apart altogether, and the two objects go their separate ways across the galaxy. Only a minority hold together, and those that do are held on terms nothing like the ones they began with. Whatever bond outlives the event has to be agreed a second time, from the beginning. A remnant thrown clear of its birthplace can travel remarkably quickly. Measurements of these objects give speeds of hundreds of kilometers per second, far above the leisurely drift of ordinary stars around the galactic center, and the swiftest examples known to us move quickly enough to leave the galaxy altogether in time. The push comes from the collapse itself. The inner region does not fall inward perfectly evenly. The neutrinos do not stream out perfectly evenly either, and the small imbalance that remains is enough to launch a body heavier than the sun like a stone from a sling. At such speeds, a runaway covers tens of thousands of light years in a few dozen million years, which, by stellar standards, is a short journey. It arrives somewhere with no obvious connection to the gas cloud that made it, among stars it has never had anything to do with. A traveler who set out owning nothing at all. In a system that stays intact, a quieter change eventually arrives. The surviving companion goes on burning as an ordinary star for a while. But stars do not keep the same size forever, and once its central hydrogen runs low, it swells outward, sometimes to many times its former width. As the outer layers expand, they reach a surface in space where the pull of the small, heavy neighbor is stronger than the pull of the star those layers belong to. Beyond that surface, the gas no longer answers to its parent. It crosses the narrow neck between the two bodies and joins the smaller one, at first as a trickle and afterwards as a steady stream. So the companion begins to lose the outside of itself without any change in what it is doing. Ownership of the material has moved, while the material stayed where it was. A border rewritten without a single word being said. Matter crossing that gap grows extremely hot long before it lands. The gas cannot drop straight down, so it settles into a broad, flattened structure around the compact object. And as it works its way inward, it gives up gravitational energy. Friction within the flow turns that energy into heat. The outer parts of the structure are merely warm by stellar standards. Yet the inner parts reach several million degrees, and material at such temperatures radiates not in visible light, but in X-rays. This is why systems of the kind are known at all. From the ground, they show nothing remarkable, while an X-ray telescope above the atmosphere sees a brilliant source where the eye finds an unassuming star. Most of the catalogued neutron stars with companions were discovered in exactly that way, by the glow of matter that has not yet reached anywhere. Here, the warmth is manufactured out of approach alone. A light donor star gives the arrangement enormous patience, where the companion weighs no more than the sun, and often rather less. The handover of material proceeds gently and can continue for hundreds of millions of years. Astronomers call these low-mass X-ray binaries, and they are among the steadiest sources in the X-ray sky. The two bodies usually sit close together, circling each other in hours rather than years, and the ordinary star is old and dim, while its neighbor is a compact remnant no wider than a city. In some of these systems, the flow scarcely stops at all, while in others it pauses for years at a time, and either way the brightness rises and falls over months as the supply varies. Nothing in the process is hurried. The donor simply hands over the outside of itself, layer upon layer, across an interval no observer will ever see the end of. A long partnership between two thoroughly unlike bodies. With a heavy donor, the feeding works along quite different lines. A star of 10 to 40 times the mass of the Sun need never swell far enough for its outer layers to cross over, because long before that could happen, it is shedding material on its own, driven off its surface by the pressure of its own light, in a wind that carries away a noticeable share of the star over its lifetime. Nearly all of that wind escapes into space and is simply lost. The compact neighbor, traveling within the outflow, captures whatever happens to pass close enough to be caught, a small fraction of the total, and still ample to make the system blaze in X-rays. Systems built this way are more erratic than their gentler counterparts and shorter-lived, since the donor itself does not last. A guest fed by the draft from an open door. Little else in nature turns matter into light so efficiently. Material falling onto the surface of a neutron star converts a substantial part of its own mass into energy on the way down, and estimates put that share somewhere between 1/10 and 1/5, depending on how the flow behaves as it arrives. Set the number beside the process that powers ordinary stars. Nuclear fusion, joining hydrogen into helium, releases well under 1% of the mass involved and takes millions of years to work its way through a stellar core. Simple falling onto a surface where gravity runs to something like 200,000 million times the pull at the Earth's does better by more than a factor of 10. This is why a body 24 kilometers across can outshine an entire star. Physics rarely offers so good a bargain. Fuel gathering on that surface does not burn quietly for long. Hydrogen and helium taken from the neighbor spread into a layer perhaps 10 meters deep, and the weight of everything above squeezes the underside of it until the temperature there approaches 1,000 million degrees. At that point, the layer ignites, more or less all at once. The brightness climbs within a second or two, holds, and falls away again, over anything from a few seconds to a few minutes, after which the star returns to what it was doing before. The layer then begins to gather afresh, and the same thing happens once more, at intervals of hours or days, according to how quickly material is arriving. Some systems have been watched through thousands of these events, a habit measured out in days and carried through in seconds. Once in a great while, a far larger event occurs on the same surface. The ordinary flashes do not consume everything they touch, and the carbon they leave behind sinks and accumulates at greater depth over long stretches of time. When enough has gathered and conditions underneath are right, that deeper carbon ignites in its turn. The result gives out roughly 1,000 times more energy than a common flash, and takes hours instead of seconds to fade, while the wait between one such event and the next is counted in years rather than days. Only a modest number have ever been recorded, which is hardly surprising given how seldom they come round, and every figure attached to them should be taken as approximate, since each occasion is a rarity rather than a routine measurement. It is a slow chapter in a book made of quick pages. During the strongest of these flashes, the star briefly loses hold of its own outer skin. Light streaming out of the burning shell carries enough pressure to push back against gravity, and for a short while, the outward push prevails. The visible surface, the thin layer from which light finally escapes into space, lifts away by kilometers and hangs there while the flash is at its height. As the burning subsides, the pressure falls, and the layer settles back to where it began, the whole excursion taking seconds from start to finish. Astronomers follow these episodes closely because the moment at which light exactly balances gravity depends on how much mass the star holds, and the way the spectrum shifts during the lift and the return carries information about the radius as well. A sky raised and lowered inside a few seconds. Every flash leaves ash behind, and the ash has nowhere to go. What burns is hydrogen and helium. What stays afterwards is a mixture of heavier elements, carbon among them, along with nuclei further up the table. Being heavier than the fuel above it, that residue sinks, coming to lie beneath the layer where the next supply is already gathering. Over thousands of flashes, a thickness of processed material accumulates below the burning zone, pressed steadily downward by everything that arrives after it, until the pressure works it into the crust proper, and it becomes part of the star's outer kilometer. Nothing ever stirs the deposit or brings it back up. It lies there in order, the oldest at the bottom, while the surface above goes on flaring and quietening as though no such archive existed. The rock builds up in layers that nobody will ever dig up. Heat from the arriving material does not stay at the surface where it lands. As the deposit is pressed downward into the crust, the nuclei within it meet conditions in which they cannot keep their form, and they react. Electrons are captured, nuclei break apart and recombine, and each of those small rearrangements gives out energy at the depth where it occurs, well inside the solid outer kilometer. Adding the reactions together, calculations give something like 1 to 2 mega-electron volts of heat for every particle that came across from the neighbor, a quantity that sounds negligible for a single nucleus and amounts to a great deal once the flow has been running for 1,000,000 years. A star fed in this manner is warm through the thickness of its shell, not merely on top. Heat put away in the walls for later use. Once the flow stops, the system becomes useful in another way. Some of these binaries do not hand over material continuously. They run for years and then fall quiet as the supply is interrupted. And when that happens, the crust, warmed through by a long spell of arriving matter, starts to give up what it stored. Telescopes follow the fading X-ray glow for years afterwards, watching the temperature come down in small steps. How quickly it comes down depends on how well the crust carries heat outward, which depends in turn on whether the material there sits in an orderly lattice or a disordered one, and on how much of it takes forms nobody can make in a laboratory. The cooling curve, therefore, becomes a test of the models. Propose a structure, calculate a curve, compare it with what the star does. A house judged by how slowly it gives up its warmth. Left to itself, a neutron star cools by an entirely different route and takes far longer over it. For roughly the first 1,000,000 years, the heat does not leave as light at all. It leaves as neutrinos, made in the dense interior and passing straight out through the full thickness of the star without being absorbed anywhere, which drains the core far faster than radiation from the surface ever could. Only when the inside has fallen well below that early condition does light take over as the main way heat departs. The timescales involved are long ones. 1,000 years after it forms, the surface is still several million degrees and shines in X-rays. Tens of millions of years further on, the same object glows so faintly that finding it at all is an achievement. The ember has a very long evening ahead of it. The soundest ages we have belong to objects whose arrival somebody happened to witness. Most ways of dating a neutron star lean on assumptions about how it has changed since it formed, and an assumption can be mistaken, whereas a written record cannot. Where a compact object sits inside the expanding shell of an explosion that was seen and noted down at the time, its age is simply the age of the observation. The one in the constellation Cassiopeia lies within a shell whose expansion points back to an event around 330 years ago. Another sits amid the debris of the outburst that observers set down in their chronicles in the year 1054, which makes it close to 1,000 years old. Such cases number a handful among thousands of known objects, and they anchor everything else. A birthday attested by the neighbors. Most routes to finding one of these objects are narrow, and a very small number of them account for nearly everything we have found. The first depends on geometry. A beam of radio waves leaves the magnetic poles, and unless that beam happens to point along the line towards the Earth, the star announces nothing whatever. The second is thermal, and serves only for young objects still hot enough to shine in soft X-rays on their own account, which excludes almost everything older than a few 100,000 years, and that is to say, the overwhelming majority of them. The third arrives as a disturbance in space itself, detectable in the final moments before two such bodies join, an occurrence so uncommon that a single detection is news across the discipline. Almost every solitary one in the catalogue has come through the first two of those openings. The pairs give themselves away by the third, or by the light of the matter falling in, and each opening admits a particular and unrepresentative sort of star. It is three narrow windows cut into a dark wall. Estimates put the number of neutron stars in our galaxy at something like 1,000 million. The figure is an estimate, and nothing firmer. It comes of working backwards from how often massive stars are thought to have exploded across the whole history of the galaxy, combined with a lifetime that for these objects is effectively unlimited, since nothing removes them once they exist. Against that stands the catalogue, which holds several thousand entries and gains more with every survey. The gap between the two numbers is not a shortcoming of instruments, but a statement about the objects themselves, almost none of which give out anything an instrument can register. Every future survey will add entries, and the share accounted for will remain so small that the arithmetic scarcely notices. A census that will never be brought to a close. Nearly all of them are invisible to us, and the reasons are well understood. The great majority formed long ago and have had ample time to cool, so their surfaces no longer glow at any wavelength a telescope can pick out. The conditions that produce radio emission do not last, and once they have gone, the star is silent at those wavelengths. They have no companion feeding them, so there is no bright inflow of matter to give them away. Nothing about such a star is broken. It is simply finished. And a finished object has no way left of drawing attention to itself. In practice, this means that the whole body of knowledge on the subject is built upon a narrow and knowingly skewed sample, drawn from the youngest, the hottest, the most strongly magnetized, and the best supplied. Almost the whole population lives without ever being seen. A few of these objects end up with a neighbor of their own kind. When a binary of two massive stars survives not one explosion, but two, and holds together through both, what remains is a pair of compact remnants circling one another, with nothing left to burn and nothing further to lose. Around 24 such systems are known within our galaxy, and given how difficult they are to find, a good many more presumably exist. They differ from every other arrangement in one respect. An ordinary binary eventually separates, or its donor is exhausted, or one member wanders away. Here, neither body can evolve any further, and neither has anywhere else to be. The two continue together over spans of time that dwarf the histories of most things one might set beside them. A pair with one very long meeting still ahead of it. A pair of these bodies, bound to one another, gives away the distance between them a little at a time. The motion itself is not free. As the two swing around their common center, the geometry of space around them is stirred, and that stirring carries energy outward as gravitational waves. Nothing returns the energy to the pair, and what leaves cannot be recovered, so the orbit answers in the only way available to it and grows a little smaller. The loss is modest by any human measure, a few meters of separation in a year, which against an orbit hundreds of thousands of kilometers across is very close to nothing. From one decade to the next, such a system looks entirely unchanged, yet the drain never pauses and it never reverses, because no mechanism anywhere in the system can put back what the waves have taken. The gap between two such bodies is not a possession, it is an expenditure. Because each year removes so little, the whole approach runs for hundreds of millions of years, and for almost all of that span, there is nothing an observer would call an event. 2 points travel their slowly narrowing circles, a fraction nearer with every turn, in a process that would have begun before the continents of the Earth had taken their present arrangement, and would still be underway after they had been rearranged again. Mountain ranges are raised and worn flat inside such a span. Whole families of living things appear and vanish inside it. The pair, meanwhile, does one thing only, patiently and without variation, and any single century of it would look identical to any other century, since the change across 100 years is less than the diameter of the bodies themselves. Nothing at all marks the passage of that time from outside. An approach can outlast most of the mountains on a planet. The final stretch bears no resemblance to the ages that came before it. Once the separation has fallen to a few hundred kilometers, the loss of energy quickens sharply, because the nearer the two come, the more powerfully they disturb the space around them. And that disturbance drains what keeps them apart all the faster. What the earlier stage needed 100 million years and more to accomplish is then accomplished again in minutes, and the last of it in seconds. The two sweep around one another with the separation falling from hundreds of kilometers to nothing, each turn following the one before it more closely than the last, until the surfaces meet. Nothing in the long ages beforehand gives any warning that the ending will be so abrupt. An age of slow drawing nearer is concluded inside a handful of seconds. Such a road can end in less time than it takes to say so. In the final orbits, each body pulls the other out of its round shape. And this is what allows us to weigh their contents from an enormous distance. How far a body yields to its companion depends on what fills its interior. A stiffer inside gives less. A softer inside gives more. And the difference alters the timing of those last turns by a small but measurable amount. That timing is written into the signal that reaches us, so the yielding can be read out of the record without anyone ever seeing the objects at all. When this was done for the event of 2017, The answer pointed towards smaller radii than a good many models had allowed, narrowing the range that theories of dense matter are permitted to occupy. Decades of argument conducted on paper were trimmed by a few seconds of data. A hardness weighed across 130 million light-years. One such meeting has been followed from beginning to end. On the 17th of August, 2017, a signal passed through the detectors for about 100 seconds, climbing in pitch as the turns quickened and then stopped. Telescopes were swung towards the patch of sky the detectors had marked out, and the source was found in a galaxy catalogued as NGC 4993, roughly 130 million light-years away, an unremarkable elliptical that had drawn no particular attention before. Within a day, observatories on every continent and several in orbit were watching the same point of light, and several thousand astronomers were at work on a single object at once. A great many arguments that had run for decades were closed in the week that followed, not by reasoning, but by looking, which is the rarer way for an argument to end. One evening answered several very old questions at once. The instrument that recorded all this measures a change in length smaller than the width of a proton. Its design is simple to describe. Two arms 4 kilometers long, set at right angles, with light sent down each and brought back to be compared. A gravitational wave passing through stretches one arm and squeezes the other by an extraordinarily small amount, and the two returning beams of light fall out of step by exactly that much. The change to be caught is a tiny fraction of the width of a single proton over an arm 4 kilometers long, which is something like measuring the distance to a nearby star and noticing an error the thickness of a hair. Everything else about the machine exists to hold its mirrors still enough for that difference to show, which is why they are built far from traffic and in pairs, so no local tremor is mistaken for news from space. A measurement finer than the thing it is measured with. 1 7/10 of a second after the waves ended, a short burst of gamma rays arrived from the same direction. Two conclusions followed from that single interval at once. Short gamma ray bursts, whose origin had been debated since the 1970s, were shown to come from the meeting of two such bodies, since here was one caught in the act, with the gravitational signal attached to it. The interval itself carried the second conclusion. A second and a fraction, after a journey of that length, means that gravity travels at the speed of light to a precision no laboratory on Earth could approach, because even a slight difference between the two speeds would have opened into a gap of centuries along such a road. The whole of that conclusion hangs on a delay a person could have counted out loud. Two messages from one event arriving 2 heartbeats apart. For several days afterwards, the material thrown outward went on glowing, and that glow had a character of its own. Astronomers call it a kilonova, a name chosen because it shines something like 1,000 times brighter than an ordinary nova, while remaining far below a supernova, occupying a place on the scale of brightness that had been predicted on paper years before anything was seen there. It faded within days, rather than the weeks or months a supernova takes, so telescopes had to be pointed quickly to catch it at all. As it faded, it also changed color, beginning blue and turning steadily redder, until within about a week it was radiating mostly in the infrared and slipping out of visible range altogether. That change of color had been predicted too, and it proved the most informative thing about the whole glow. The light changed color as it went. The reddening happened because the heaviest elements in nature were being assembled in the debris while it shone. Conditions there were extraordinarily rich in free neutrons, and a nucleus sitting in such a flood takes them on faster than it can decay, absorbing one after another in quick succession and adjusting afterwards by shedding electrons. This is the rapid capture process, and it builds its way past iron and up through the heavy end of the periodic table in a matter of seconds. The elements it produces are large, complicated, and extremely good at absorbing light, which is precisely why the glow turned red. The freshly made material blocked the shorter wavelengths and let the longer ones through. Where in the universe this process takes place had been an open question for half a century, and the answer arrived in a shift of color. Chemistry had finished before anything had a chance to argue. Estimates put the amount of gold made in that one event at roughly the mass of the Earth. The figure deserves its qualifier because nobody weighed anything. It is drawn from the brightness and the color of the fading glow, compared against models of how much material of what composition would produce that particular curve. Different groups working from the same data arrive at answers that differ by a considerable factor. And the honest form of the statement is that the quantity was enormous, and the precise number depends on the model chosen. Platinum came out of the same seconds, and uranium, and the whole heavy tail of the periodic table. Whatever the true amount, the manufacturing run was brief, and that pair will never produce another gram, there being no longer a pair in that place to do the work. A shop window filled once, and then closed for good. Everything produced there leaves the neighborhood and stays in the galaxy. The debris departs at a good fraction of the speed of light, in tenths rather than hundredths. And nothing stops it, because there is nothing out there able to stop it. It spreads through the thin gas between the stars, slows over long ages as it sweeps that gas along with it, and mixes into the clouds where new stars are assembled. Some 100 million years later, or a great deal more than that, the material is drawn into a collapsing cloud along with everything else, and becomes part of a new star, and part of whatever planets gather around it. The atoms carry no record of where they were made, which is why the connection had to be worked out rather than simply seen, element by element and model by model. The parcel is passed on with no return address on it. The heavy elements in the ground beneath us are older than the sun. Nothing inside the sun makes gold, and nothing inside the earth makes it either. Both formed out of a cloud that already contained it, manufactured elsewhere and delivered long before either of them existed. Every gold atom in a ring or a coin or a circuit board was put together in seconds, somewhere else, under conditions of a kind we have now watched exactly once, and perhaps in one or two other kinds of event that we have not yet caught in the act. It then spent an unmeasured stretch of time adrift in the galaxy before the cloud that became the solar system gathered it in. The same holds for the platinum in a catalyst and for the uranium warming the inside of our own planet. Among the objects a person is able to pick up and turn over, these have the strangest history of all. A very old debt, worn on the fingers. When two of them finally meet, what is left is either a heavier body of the same kind, or no body at all. And which of the two depends on how much material was there to begin with. If the combined mass stays under the amount that such matter can support, the remnant is another object of the same nature, hotter and larger for a while, easing towards the ordinary condition over the following minutes. If the combined mass is above it, the arrangement cannot be maintained, and what is left closes into a black hole. The signal from 2017 points to a history between the two. Something is thought to have held itself together for roughly a second, long enough to leave its mark on the debris, and then gave way. Both endings had been argued for on paper long before anyone was able to watch one happen. A limit reached 1 second after a very long road. A limit certainly exists, and where exactly it falls is not something anyone can yet state. It sits somewhere between 2 and 3 times the weight of the Sun. Modern estimates cluster near 2¼ and several independent approaches have converged towards that neighborhood, though the value is not a constant of nature in the way the speed of light is. It depends entirely on how matter behaves at densities we can neither produce nor examine, which is the one thing about these objects we do not know. A stiffer interior carries more weight and pushes the limit upward. A softer one gives way earlier. Every new weighing of a heavy example narrows the possibilities a little from below. The number is therefore a statement about our ignorance wearing the clothes of a measurement, and it will move as that ignorance shrinks. Everyone agrees the border is there, and nobody can draw it. The heaviest of these that we have measured reliably carries about 2 8/100 times the mass of the Sun. Its weight is known that precisely because its companion passes almost exactly between it and us. So the light traveling towards us is delayed by a measurable amount as it climbs out through the companion's gravity. And that delay converts directly into a mass. The same object has had its radius measured as well, at about 12 4/10 kilometers, with an uncertainty of roughly a kilometer either way. That combination of a very high mass with a modest radius is among the strongest constraints we hold on what fills the inside of such bodies, since any account of dense matter must be able to support that much weight in so little space. It leads the list only in the sense that nothing heavier has yet been weighed. A record standing at present, kept without any noise about it. Between about 2.5 and 5 solar masses, our catalogues are very nearly empty. Below that stretch, we find the objects this whole account has been about, with something over 100 of them weighed individually. Above it, we find black holes of the ordinary stellar kind, appearing in growing numbers as the detectors improve. In between, there is a shelf with almost nothing standing on it. Part of that emptiness may belong to nature, a consequence of how collapsing stars divide up their remains, leaving the middle range rarely occupied. Part of it is very likely a matter of detection, since objects of that weight are awkward to find by every method available to us, and a gap in a catalogue is not the same thing as a gap in the universe. The newest instruments have begun to place 1 or 2 entries on that shelf, which is itself worth knowing. The shelf holds almost nothing at all. Crossing that limit does not look like an event. Nothing is announced. One further spoonful of material arrives on a body already carrying its maximum. And from that moment, nothing inside is able to hold the weight. The interior is already as unyielding as neutrons pressed together can be made, both by their refusal to share a state and by the force between them. And past that point, no further reserve can be called upon. No firmer arrangement waits underneath to take over. The surface, therefore, continues inward, and what had been a body 24 kilometers across becomes a black hole with no outward sign whatever. No flash accompanies it. No signal of any kind escapes to mark the change, and an observer at a distance would notice only that a faint source had gone quiet, and had stayed quiet afterwards. The largest change of state available to matter is also the quietest. A threshold stepped over without a sound. Whatever remains on this side of the limit has an exceedingly long cooling ahead of it. The heat of formation goes first, carried away by neutrinos through the interior, and afterwards more slowly as light from the surface. After tens of millions of years, the surface has fallen below 100,000 degrees, which sounds warm and is nonetheless dim for an object so small, and its radiation has moved into wavelengths that no telescope yet built could pick up at any useful distance. The cooling continues regardless, through ages far longer than the one just described, and at no point does anything about the structure change. The density on the last day is the density of the first. Such a body does not shrink as it cools, does not spread out, and does not alter in any manner an observer could see. Only the glow is subtracted. In the far future, when star formation has ended, and the last of the long-lived stars has gone dark, these objects will still be there. What holds them up owes nothing to heat, which is why the end of the stellar era makes no difference to them. Their support comes from a prohibition against particles sharing the same state, and from the force between the particles themselves, and neither of those cools, runs out, or weakens with age. Ordinary matter in that era will be cold and thinly spread, the galaxies scattered, whatever light remains coming from nothing in particular. Through all of it, these bodies will keep the same diameter and the same density they had, while the sky was still full of stars, dark and unaltered, carrying the shape of an era that has otherwise ended. They remain the last hard things in a very soft world. Everything described here has been one substance that ran out of room. Ordinary matter is almost entirely empty space, a scattering of nuclei with electrons held far away from them. And that emptiness is not a property of the material, so much as a privilege granted to it by circumstance. Remove the privilege, press hard enough for long enough, and the emptiness is withdrawn, leaving only what was ever actually present. The layers, the ocean under the crust, the fields, the flares, the slow approach of two bodies across enormous ages, the boundary past which the arrangement cannot be kept. Every one of them follows from that single withdrawal. No additional ingredient appears anywhere in the account. The whole of it is the ordinary contents of an ordinary star, with the gaps taken out, which is also, in a small way, a description of everything else. An ending that is also the smallest possible beginning. We began with a fall that stopped. A star that had held itself up for millions of years came to the end of its fuel. Its center dropped inward in less than a second, and something in the nature of neutrons declined to let it go any further. From there we went downward through the layers, through an atmosphere no deeper than a few centimeters, across a surface smoother than anything ever polished in a workshop, into a crust of remarkable strength, and deeper still into a sea that flows without friction. We came out to the fields, some of them steady, some of them strong enough to rearrange themselves in a single quiet moment. We looked at the ones that live in pairs, feeding, brightening, warming their surfaces on a companion's material. And we finished where such pairs finish, with two of them coming together after an age of approach, with the metals that meeting scattered across the galaxy, and with a boundary beyond which this state of matter is no longer held. All of it comes from one small circumstance. The material around us and in us is mostly empty space. And that emptiness is only ever on loan. Where it is called back in, this is what is left behind. Something the width of a city, denser than any other material we know of, dark and utterly silent, doing nothing whatever for longer than the stars themselves will last. If this is the kind of quiet you would like more of, the subscribe button will be waiting whenever you want it. Sleep well tonight.